So we have some tangent line theorems. Now, first thing, let's recall what a tangent line is. So a tangent line, remember, is a line that's going to touch your circle in exactly one spot. So that means it's just going to touch the edge in one spot. So it's going to always look something like if you have your circle, it's going to be touching the edge and it's only going to hit in one little spot. And remember, that little spot is called the point of tangency, wherever it hits. So we do have two theorems about that we're going to talk about. The first theorem is that tangent lines are perpendicular to the radius. So perpendicular to the radius at the point of tangency. So at that little dot right there. So let's take a look at the picture that we have here. So it says, if the line segment JK is tangent to circle L, find the value of x. So if we take a look at this, so let's take a look at it says that if we have a tangent line, so this is a tangent line right here. So it's only going to touch the circle in one spot. So the point of tangency is right here at J. That is your point of tangency. What this is saying is that this is going to be perpendicular to the radius. So remember, this is my radius right here. So my tangent line is perpendicular to it. So we know perpendicular means it's going to form a right angle right there. So what has happened here is we've formed a right triangle. So we know if we have right triangles, then we could use SOHCAHTOA, right? If we need it. SOHCA. Oh my gosh. I better actually spell that correctly. Let me go back. Undo. I'll write it over here. So, oh jeez, so, ka, to, and we also have the Pythagorean theorem. So these are two things that we can always use whenever we have right triangles. So whenever you see right triangles, just ask yourself, are either of these items going to help me? So what we're looking for is the length of x right here. So we have two of the sides and we need to find the third side. So that means that Pythagorean theorem is going to be our best option at this point to find our third side. Because SOHCAHTOA in this case might find us some angle measures, but then we're not asking about that in this problem. So let's go ahead and use this right triangle. Now remember that Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the legs and c has to be the hypotenuse. So that means our 7 could be our a, our 19 could be our b, and our c is what we are missing. And remember, a and b could be backwards. So 7 to the second power is 49 plus 19 squared is 361, and that equals c squared. Add these like terms, grab your calculator. I get 410 equals c squared. And then in order to get c by itself, we have to take the square root of both sides. So I'll put that in your calculator. Square root of 410 is approximately 20.25-ish. 20.25. So that means that x is equal to about 20.25. Let's put that on our picture, 20.25. Does that make sense? We've got a 19 and a 7. 20 has to be the longest side, so that does make sense. Let's look at the next one. So the next theorem we have is that tangent lines from a common external point are congruent. So a common external point means I have some point out here in the sky, and I have two tangent lines that come and touch it. So I have this tangent line and this tangent line right here. Those two lines are going to be the same length, congruent. So from two tangent lines from a common external point are congruent. So that means that this piece is congruent to this piece. So we know congruent means equal in measure. So that means we could set those two pieces equal to each other. So we can set 4x minus 9 is equal to the other piece, which is just 15. And then I could do my little algebra and solve that. Plus 9 on both sides. I get 4x is equal to 26. 24, my bad. 24. And then I'm going to divide both sides by 4. And I'm going to get x is equal to 6. And I could double check that in this problem. If I plug a 6 in right here, that's a 4 times a 6. That's a 24. Take away 9 does give me 15, so that's good. Now here's the deal. You could have actually figured this out without this theorem, because take a look at this. What if I were to connect these? Between any 2 points exists only one line. This right here is a radius, and this is a radius, right? And so that means this piece must be congruent to that piece, because they're both radii of the exact same circle. So if I take a look at this, I would have a right angle, correct? And I would have this in the middle. Remember, that's reflexive property. So I actually could prove these triangles congruent without having this blue piece. I could say these two triangles are congruent by, remember all of our theorems you could use. Remember, you could use side, angle, side, or side, 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 or angle, angle, side, or angle, side, angle, or hypotenuse, leg. So if I take a look at these two triangles, even if I didn't have the blue in this theorem, I could say I have a right angle because these are both tangent lines. So the tangent and the radius do form a right angle. So I have my right angle. I have all radii of this circle are all congruent in length. So I would have reflexive property in the middle. So I would actually have hypotenuse, leg, right angle. So these two triangles are congruent by hypotenuse, leg, right angle. And then I would be able to prove these two blue ones are congruent by corresponding parts of congruent triangles are congruent. So I didn't even actually need that theorem. I could have done it using congruent triangles. Remember, make sure these two examples do get cut off of your paper and glued into your notebook. And then the rest of the problems are your practice problems.